आफ्टरनून स्टूडेंट्स, आज आपको मैं सेकंड ऑर्डर रिएक्शन की काइनेटिक्स और रेट इक्वेशन के बारे में बताएंगे, रेट कांस्टेंट के बारे में। और एज यू ऑल नो, सेकंड ऑर्डर रिएक्शन कैन बी ऑफ टू टाइप्स, वन इन विच द कंसंट्रेशन ऑफ बोथ द रिएक्टेंट्स इज सेम and the another one in which the concentration of both the reactions is different. So today I will be telling you about such type of reactions in which the concentration of both the reactants is different. So we all know this, we have already done this type of second order reaction in which the concentration of both the reactants is same. And today we will take up this type of reactions in which the concentration of the reactants is different. So come on, let's start with it. Suppose we take this type of reaction in which the two reactants are A and B, and let us assume that the concentration of A, initial concentration of A is this small a, and the initial concentration of B is small b. Initial concentration means when the reaction is just about to start at time 0. So after time t, what will happen? Some amount of A and B will decompose and it will form product, and let the amount of product formed, the concentration of the product formed be x moles per liter. So the amount of A and B left will be A minus x and B minus x moles per liter. Okay. Now the rate of reaction in terms of the differential rate of reaction in terms of products we will have to calculate, and that is given by dx upon dt. Let us assume to be equation number 1, and the rate of reaction in terms of the order, that will be given by the product of the rate constant and the concentration of A and concentration of B. This is the concentration of A after time t, and this is the concentration of B after time t. So this will be our rate of reaction. So we are having two equations which are depicting the rate of reaction. And since both are depicting the rate of reaction, we can equate them. When we equate them, we get this equation: dx upon dt is equal to k, A minus x, B minus x. Equation, let it be equation number 2. Now a bit of rearrangement is done over here, and we get it in this form: dx upon A minus x, B minus x is equal to k. Now what we do to solve it out, we will have to integrate it, but we cannot integrate it in this form. It is 1 upon A minus s, B minus s. So what we do is partial fractionation of this term. And how do we do partial fractionation? This I will tell you over here. So now I have written this equation number 4, this side of the board, to get more space for me. So we are having this equation. Now to solve this equation, we have to integrate it. And to integrate, we can't integrate in this fashion. We have to do the partial fractionation method. Come on, let's do the partial fractionation method of this left hand side of this equation. So I will take only the left hand side of the equation, which is given by 1 upon A minus x and B minus x. So first of all, we will do the partial fractionation of this. So we can write this in this form: P upon A minus x plus Q upon B minus x. And now we will first of all find the values of P and Q. Simple calculation over here. This will come in LCM: A minus x, B minus x, and here we will be having P into B minus x plus Q into A minus x. And this is equal to 1 upon A minus x and B minus x. Now we are having A minus x, B minus x over here, and here also we are having A minus x and B minus x. And this is the equal to sign. So we can easily cancel out these two terms from here and here. Now what remains is, we will open the brackets over here, and what we get now is 1 is equal to Pb minus Px plus Qa plus minus Qx. It's very simple. We have just opened the brackets. Now we will bring these x terms. There are two x terms. We will bring them to one side, and what we have is minus of px minus of qx plus of pb and plus of qn. So this will be equal to, we take the x common and out of the bracket, and minus x we take out of bracket. What remains is p plus q inside the bracket plus this term pb plus qa. Okay. And this is equal to what? This is equal to 1. Now we can write 1 in this form also, minus x multiplied by 0 plus 1. If you calculate it, it will come out to be 1. And this we are doing it to simplify so that we can arrive to some conclusion. We can solve this equation. We are bringing it in this form. 1 can be written as minus x 0 plus 1. Or you can say minus x multiplied by 0. Okay, and placed it in bracket. This means minus x multiplied by 0 is 0 and plus 1. So this is another form of writing 1. This we are doing it to solve this equation, to arrive to some conclusion. So this will be equal to, now you just have a glance at it. This is minus x into 0. Minus x 0. This corresponds to, let me take a different term. So I will write it in this manner. So this is minus x 0 plus 1. Minus, if we compare it with this, what is minus x multiplied by 0 plus for this 1. Okay, this is the most crucial thing if you can understand it. This is 1, this was initially 1, and this is also 1, but we have written in a different form just to arrive to some conclusion and to solve it. So we have this minus x, so this x is x over here. This 0 corresponds to this p plus q is 0, and this 1 corresponds to this pb plus q. Okay, so we are having p plus q equal to 0. P plus q equal to 0. This means that p will be equal to how much? Minus of q. This is our one relation in which we have got the value of p, which is equal to minus of q. Now let's see another relation. pb plus qa is equal to 1. So pb plus qa is equal to 1. Okay. Now we are having the value of p over here. What is the value of p? P is minus of q. So it will be minus of q multiplied by b plus qa. This is equal to 0. Or we can write it in another way, that we can write it in another way, that qa minus of qb will be equal to 0. Okay? Okay? No, sorry, is equal to 1. This is 1. Is equal to 1. This means that q is common in both the things. So it will be q a minus b is equal to 1, and the value of q comes out to be, here I will write it. The value of q will come out to be 1 upon a minus b. So we are having the value of, now we have the value of p, and we are having the value of q also. So if this is the value of q, then what will be the value of p? From here we will get the value of p. P will be equal to minus of q, and that will be minus of 1 upon a. Minus of 1 upon a. Okay. Now we will substitute these values in this q and p and q in this relation. Let it be relation number 5. Let it be relation number 5. Now we will substitute these values of q and p. Q is 1 upon a minus p, and p is 1 upon a minus p. Now we will substitute these values. These are the values of p and q, and let us substitute in equation number 5. So we have, let me make a boundary. So we are having p, the value of p is 1 upon a minus b, 1 upon a minus b, and what we have here is 1 a minus x over here, and then we have this plus sign, plus, and what is q? Q is 1 upon, sorry, this was minus 1 upon a minus b, and q is 1 upon a minus b. So it will be 1 upon a minus b multiplied by a minus x. We can see that a minus b is common. So what we will do is that we will take out a minus b outside the bracket as common, 1 upon a minus b as common, and what remains inside is, we will take this term first. This is actually 1 upon a minus b, this is b minus x, okay? This is b minus x. So we take 1 upon a minus b as common, and what remains is minus 1 upon a minus x, minus 1 upon a minus x, and plus 1 upon b minus x. I have done this rearrangement in this single step. Okay? I have brought this minus term over here and this plus term over here. So we are having finally this equation. And if we compare this equation number 11 to equation number 6, and if we compare it with equation number 4, so what we have to do is that we have to integrate it now. Okay? And the boundaries being x equal to 0 and x equal to x, and time is equal to, and the bounds for the time will be t equal to 0 and t. So in fact, if we compare with that equation number 4, if we bring it to that, in that condition, then it will be 1 upon a minus b. We have to integrate this whole equation, 1 upon b minus x minus 1 upon a minus x into dx will be equal to how much? K dt. K 0 and t, the limits are 0 and t, and here the limits are 0 and x. Okay? Now we have to integrate it. We will integrate both these terms separately, and since a minus b is a constant, it will be out of the integration limits. A minus b is constant, and what we have inside is 1 upon b minus x dx. Okay? Integration of this term minus integration of the other term 1 upon a minus x dx is equal to, if we integrate it, we have seen it many times, the value of this will come out to be kt plus c. Okay? And c is the constant of integration. It's very common, you all know about it. So let's take it as, let's solve it in the single step, kt plus c. Okay? Now come to this left hand side of this equation. So what we have now is, we all know the value of integration of 1 upon b minus x dx. What will be the value? The value will be log natural b minus x with a negative sign, since we are having a negative sign to this x. So it will be log natural b minus x with a negative sign. So let's come over to this equation, a minus b, and what comes over here is minus log natural b minus x. Similarly, this I will first write this minus sign. Now we will calculate this also, and this will come out to be minus of log natural a minus x. This will all will be equal to how much? kt plus c. There is less space, and I am trying to save the space now. And this is minus and minus. Minus and minus will become plus. Okay. So I will do it in a single step. Let it be plus over here. So what we have now is 1 upon a minus b. Inside the bracket we have log natural a minus x minus log natural b minus x. Okay. This all is equal to kt plus c. Now we very well know the property of log. You know this property of log, which is that log of n minus log of n. This is actually log of m upon n. Okay, we all know this property. We will apply this property over here, and this is actually natural log, and when we have to change it to log base 10, then we have to multiply it by 2.303. So we are having this equation and we will apply this property of log over for these two terms, and what we have is 1 minus a minus b. Okay, this 1 upon a minus b, and in the bracket we get this is actually log of a minus x minus log of b minus x. So what we will have is log of a minus x divided by b minus x. Okay. Bracket closed, and this is equal to kt plus c. Now we will apply the boundary conditions, that when time is 0, then x is equal to 0, and when time is t, then x is equal to t. So for that I need space. Let me rub some parts of it. Now let's come over to this. We will apply the boundary conditions and find the value of c over here. Okay. So we are having this 1 upon a minus b. When t is equal to 0, then x is equal to 0. These are boundary conditions. We will apply over here and find the value of the constant of integration c. So what we have is log natural a minus x a minus 0 divided by b minus 0. Okay, since x is equal to 0 and t is equal to 0, and this all will be equal to k multiplied by 0 plus c. So this is our value of c, which is 1 upon a minus b log natural a upon b is equal to k multiplied by 0 will be 0. So this is our value of c. Now we will place this value of c in equation number 7. What we get is 1 upon a minus b log natural a minus x upon b minus x. Okay, this we are taking from there only. This will be equal to k plus the value of c we will place over here now. 1 upon a minus b log natural a upon b. So we have this value of this value. When we place the value of c in this equation number 7, we get this equation number 8. Now we will do a slide of rearrangement. We will bring this to this side so as to get the value of k and the t over here. So when we bring this value of c to the left hand side, it will be equal to the negative sign. So what we have over here is 1 upon a minus b log natural a minus x upon b minus x minus 1 upon a minus b log natural a by b. Now I have earlier told you the property regarding log of n minus log of n will be equal to log of m upon n. We will again apply this property over here. Since we are having this in this form, 1 upon a minus b, 1 upon a minus b will be common, so we will bring it to the outside the bracket. Since it is common, we will bring it out. Okay, and we will place it in a big bracket over here. Now we can see that we are having this log of a minus x upon b minus x minus log of a upon b. We will apply the property of log of m minus log of n is equal to log of m upon n. And when we apply this property, what we get is 1 upon a minus b is common over here, and inside the bracket we will be having log of a minus x upon b minus x divided by what? A by b. Okay, and when we will solve, this will be equal to how much? Kt. This kt is coming from here. Let it be equation number 10. And when we solve this thing, what we will have is b upon a. Is it clear? B. So this comes out to be the value of kt. And suppose we have to calculate the value of k, then it will be, we will bring T to this side and it will be 1 upon T multiplied by A minus B. Another bracket we will keep this ln of B upon A, B multiplied by A minus X and upon B minus X. Bracket closed. So this is our value expression for the rate constant. For a second order reaction which is having in which the concentration of both the reactants is different, then the expression comes out to be K is equal to 1 upon T, A minus B, log natural B upon A minus X upon B minus X. So this is our expression. That will be equation number 11. So this equation number 11 gives the expression for a rate constant for a second order reaction in which both the reactants have different concentration. Now one more case you can see over here from this equation number 11. You can infer this. Suppose if A is present in excess quantity compared to B, then this reaction will turn to be a reaction or this equation will turn to be a equation for a first order reaction. Suppose if A is very in a huge amount compared, the concentration of A is very large compared to the concentration of B, then we can cancel off this B will be very small compared to A. We can ignore this B. Moreover, we can ignore this X also. Then in that case the equation will turn out to be 1 upon T A log natural B upon A into B minus X, and that is the equation for the first order reaction which we have studied. So this is our expression for a rate constant for a second order reaction in which the concentration of both the reactants is different. So that's all for today.